Maybe pass it around then. You earn at least one.
I don't want that pie.
You don't want chocolate?
Pie? We're talking about the pies earlier.
Yeah.
I'm worried about that.
Okay. Right, I'll leave them there for good questions. Actually, Claire had a good question with the tolerance. I never got back to doing
Excellent. Did they ever use you for the non-vector images?
No, is it because you're pretty? That's
What I did is I just mentioned the MCU to that, and that was the meeting done.
Oh, that's all your meeting's done. Seriously, that is basic management of map 101.
Actually,
If you've done the whole Firefox, I think it's a load of rubbish. I'm glad they got rid of it. Not Firefox, Firefly.
Oh, no, the other thing I did is I mentioned make files. I was like, I really want to get a good make file for my to compile my duplicate, and that was another 15 minutes right there. You know about one.
Oh, you get that one for freebie. Little gift.
So it was a good win too, so I couldn't get Gary onto that.
What's this?
Poor Power won on the weekend, so I couldn't get Gary onto that. It was a good tight win, it was well played well. I couldn't just go, it was a rough game, wasn't it? That doesn't work. So said they looked at me and went, is that really all the work you did?
Yeah, there's no worse than you try that one. With me and Paddy, it was like, do you know any sporting event at all, Paddy? No. Okay. Better do some fucking work then. Well, wait for people to arrive. Your assignments are marked and back with you. You should find that if you go back to your original assignment, the PDF, when you click on it, I've annotated it in lots of places and given you feedback. It's worthwhile going through the feedback. I don't always take off marks, but I do mention stuff. So for example, some of you decided that from now on tables and figures don't need captions. That was a second year thing. Why would you keep that going now? Because you always give a caption. So you lose a mark, but you don't lose the same mark twice. So just because you only lost one mark doesn't mean you somehow got away with the captions. Tables need captions, figure need captions, code needs comments. And not just a comment that says things like stuff what I did, but actual proper comments. But anyway, so you should have annotated. Please go through the annotations. Because even though I won't take off the same mark twice in the same assignment, I will take them off in the next assignment if you forgot them. Also, you should find that I also uploaded for each of you a mark scheme. What the mark scheme does is it shows you what your totals were, the breakdown of the marks. Also shows you how you did in the various components of the course. So the various content areas and also the various types of questions. The idea being that you can look at this as the semester goes on, and if you're having difficulty in one facet of the course, then you know where to focus your attention or come and see me. Generally, you all did really, really well. I didn't have any major problems. You seem to have done very well, especially with the R code. I know that last question was probably very new for a lot of you, so I was very impressed. Cool. As always, if you think that the marking was done by highly trained monkeys and they got it completely wrong, please feel free to come to the highly trained monkey and argue the case. The assignments are formative assessment. I take marks off to teach you a valuable lesson, i.e. you shouldn't lose the same mark twice. But once you've learned that lesson, if you come and talk to me and say, seriously, that was a bit harsh, well, we can discuss it. But the main thing is they are prepping you for your exam, which will be at the end of the year, the semester, which will be 70%. So, we're going to talk again, this is going to be a little bit of a recap. We're going to talk about model selection and just go through it again, just so we're all up to date. So in the regression setting, the standard will be something of this form. We have some predictors, x1 and xp, and our y is going to be a linear combination of these plus some noise term, and we usually fit this via the least squares. All good, we just keep coming back to this. But we're going to look at some alternative ways of dealing with that, and why would we bother? Why do we do things like, model selection, subset? This week we're going to start doing ridge regression, lasso, shrinkage estimators. Well, first of all, If n, your number of observations, is a lot greater than your number of predictors, you have no problems. That works really well. You find that your estimates have nice low variance, all good. But as we get to the point that we don't have many observations compared to the number of predictors, things start to get a problem. You say, well, that's not really a problem. We always have lots of observations and no predictors. But that's not the way modern data looks like. The classic example would be genetics. With genetics, they will come along and they'll have a thing like a microarray. A microarray is a little slide, and it has little dots. Each dot represents a gene, and what they do is they can measure gene expression. And they'll often do something like 27,000 genes on a single slide. And you think, that's brilliant, 27 pieces of information. No, it's one shit experiment done 27,000 times. It really is a matter of often, and you have to explain very carefully to your collaborators, because they'll go, I gave you 3 gigs of data. And you go, yes, but each observation was based on just 8 samples. The fact that you've got 27,000 genes, 27,000 predictors for 8 samples is a problem. So these are big problems nowadays. So if n is not much larger than p, we can start getting a fitting for prediction. If p is greater then we no longer have a unique fit. And we have to think about how we're going to deal with that. So we can compensate. Well, first of all, you can do things like you can constrain or you can shrink the estimated coefficients, which we're going to talk about later this week, with regression and lasso regression. The other fact is, if you have lots and lots of predictors, it makes your model really hard to interpret. Shrinking it down makes it easier. Coming along and going, yeah, what predicts this actual, in Ailine's case, she's looking at sepsis. What predicts sepsis? Well, here's a list of 300 genes. Means nothing. Going, well, actually, here's a list of just 10 genes, and all these genes are associated with the immune system, suddenly means something. So if you can reduce it down, and as he said, sometimes we end up with irrelevant variables in the model. That is, they don't make much difference to the prediction, but they're still significant. Can we somehow shrink it all down? So the first one we're going to look at is subset selection. This is an introduction to this whole concept. It should be a recap. There's nothing wrong with a recap. So the first one you can do is what is called best subset selection. So what we're going to do is you're going to start, you've got p predictors, and we're going to start by fitting a linear model for each possible combination of p predictors, and then choose the best model. Now, obviously, you want to, if you have p predictors, you can have 2 to the p possible models. That gets too big so fast. So the algorithm they suggest reduces that a little bit. So what we do with best subset selection is you start with the null model that only has an intercept. And then what we do is you go, right, I'm going to choose all the models with just one predictor. And I'm going to look at them quickly. So you can take all that, there'll be p models. And for each of them, I'm just going to quickly choose which is the best model where you just have one predictor. Now I'm going to choose all models that now have 2 predictors, and exactly 2 predictors. Look at all of them, work out how many, and then go to 3. And each one, what you're doing is you're just choosing the best with that number of predictors. And then finally, you'll take each of them models. So you have the best model with 1 predictor, the best with 2, the best with 3. And then I'll just compare them. And I'll do a quick comparison the first stage. The first stage, I'll probably do something as simple as RSE, or largest R squared. And so I'm going to end up with p models. And 0 will be just one intercept. Next one will just have a single predictor, another predictor. And then models I will use things like cross-validation, CP, that's Callow's P, we'll talk about that later today. AIC, BIC. Okay. So let's motivate this with an example. So we're going to look at the miles per gallon data set, which remember is a built-in data set in the tidyverse, and it just looks at various cars, and it looks at things like miles per gallon, year, cylinder, all these things about cars I understand because I don't get cars. But I know they can be different colours if that helps. Now, how are we going to do this? There's different ways you can do this. You can actually write this by hand, but I'm following the James et al. Textbook, and there they use the LEAPS package, which I thought I may as well follow that, so you've got something to follow up. Remember, if you've not been looking at the James et al. Book, it's available through Canvas. It's a PDF for you. At the end of each chapter, and you'll find I'm following the chapters pretty closely, there's a whole lab. What I mean by that is they just sort of repeat what they've done in the chapter, but give you all the R code. So it's nice to look up. Also, you can go and download the code itself from their textbook website. So then, so what I'm going to do is I'm going to look at CTY, which is your city fuel efficiency. And I'm going to start just with 3 predictors. You could have a lot more, but I just wanted to get it to fit on the slide. So I'm going to consider displacement, the number of cylinders, and the year of the car. So I'm using this function called reg subsets. So if you just use reg subsets without any sort of parameters other than your formula and your data, it does this best subset modeling. So what you can do now, if you look at the summary, what you've got here, if you come down to the bottom, is you can see you've got a rows called 1, 2, and 3. And what one is return the best model with a single predictor. So in this case, the best model with a single predictor just has cylinder in it. Then the next one called 2 says what's the best model when you have 2 predictors. And in that case, it ran through them and said, right, the best one is just displace and cylinder. And finally, the best model with 3 predictors turned out to be all 3, obviously. So it actually just quickly does it. It's very nice. It's just single command. It just goes away. You can limit. You can say, I want up to 20 predictors, and it will just spit out this big, long thing with the best model with 1 predictor, 2 predictors, 3 predictors, 4, etc. Then once you've got these models, you can grab them out. You can just say, well, give me the BIC from that, and give me the R squared. And so there you've got model 1, 2, and 3, which equates to what we saw before. And you can see, if you remember the BIC, the smallest is what you want. Row 2, the one with -2, 4, 1. It's the smallest BIC, that's your best model. So you run this first of all, and it spits out altogether K models. 1 for each, where you have the exact number of predictors, and then from that you can then use cross validation or something just to check them. Done. And once you decide on the model, we decided by looking at BIC that the second model was best. You don't have to rerun the model, you just type in your coefficients with your model. You say I want the second model, and it spits out your coefficients. Let's look at something bigger. So the package that goes with the textbook, which is James et al., so it's the ISLR package, has built-in data sets. And this is, because I didn't know about cars, let's go about something I really don't know about, so now we're going to look at baseball. So it's a thing called Hitters, and what Hitters has is, in 1986-87, they looked at the entire baseball in, I believe, a country called America. And what they looked at various predictors, and what they wanted to predict was, what was your salary? And there's all these different measures. So what I've done now is I've got Hitters full, I'm doing my reg subsets. My response variable is salary. Tilde dot says basically use everything else in that data frame other than salary. That's what the dot means. But data equals Hitters, and it goes away, and it's got this nice little plot. So if you go plot Hitters full, in this case, it returns this little square plot where it's ranked them, so it's put the best model at the top, and then it's basically decreasing. It's got the top 8 of the models. And for each of these models, okay, for each of these models, it will tell you if that variable is in that model. So it's chosen for each of these ones, each of this one, and then it's ordered them by BAC. So you can see the top model has an intercept. It's got at-bat hits, it's got walks, it's got CRBI, division W, and putouts.
And so what are those variables correspond to?
Measurements on the individual baseball player. So I'll go through them all in detail. The at-bat means the at-bat. The hits is how many times they got punched because they missed the ball. We'll go for that one.
Yeah.
The walks is if they went walking. Maybe they like, the weekends, a nice little walk. Obviously it takes into account how far you go. The CRBI, that's the, and you'd be amazed, that's the continuous red bed index. So it takes into account how many of them continuously slept in a red bed. You wouldn't think that'd be a really good predictor. It just turns out, data doesn't lie.
Well, what's division W then?
Well, that's one just above division V. No idea. Go and have a look at the thing. Go and type data Hitchens question mark, and it'll tell you all about it. I should know it because baseball is one of the biggest sports for statistics. Cybernetics was basically invented to analyze baseball. Not Matt Silver. Who wrote The Signal and the Noise? Does 538? Nate Silver. Nate Silver originally started in baseball. So it is a big, big area. It's just that I have no interest whatsoever in it. It's rounders for people being paid lots of money. I do apologise if anyone here is a baseball player, but you're mathematicians in this room, you're not. So it's a nice summary. So I've never seen this before. It's a quick way of getting your model. I've always done GL multi. The nice thing about this is I just install the package and it ran. GL multi is the package I've always used for multiple comparisons. It works really, really well. But you have to get Java to work on your system and then get ARM to recognize where Java is on your system. And it's always been jiggery pokery. Well, this worked really nicely. Okay, so let's go now and say, what about stepwise selection? So forward. So this time, we've got M0 is our null model. And what we're going to do is we're going to increase it one predictor at a time. So we start by saying, let's add each predictor at a time and find which one will augment what we had before with one additional predictor. So I can add in one additional predictor. So I'm doing a greedy forward step algorithm. So I start with a null model, I go and predict, I try them one at a time, and I say, out of all these one, which has the smallest RSE, root square error, or which has the largest R2, don't mind, that's a good one, keep it. Now it stays in the model. It's not like before where I went to it and said, right, let's look at all the ones with two predictors. Now I'm going to say, let's look at all the ones with two predictors that had the one we just accepted in the previous step. You build up, you end up with all these models, so you'll get one with no predictors, one predictor, two predictors, three predictors, but now they'll all be nested within one another. Before it didn't necessarily have to be the case. You could have one with three predictors that somehow maybe didn't have the ones before. This is not going to be the case because you start by taking a step forward. You're reducing your model space that you're exploring. How'd you do it? Basically, reg subset again. There's my full model. There's my data. I go method equals forward. You notice it doesn't look a lot different. Here's your first model. It started, it said, from the null, the best predictor to add was cylinder. And then it said, now, of the two that are left, the best to add is displacement, and then finally you add year. So again, you can step forward. Backwards. You start large and you go down. So you start with your fullest model, and you basically say, can I kick a predictor out? Yes, fine. Let's go down. I've got only k minus 1 predictors. Can I kick out a predictor? And I go down, and I keep doing that one by one. Again, at each point, I will find the best model, and then I'll compare all them at the end. Obviously, you can always do forwards. You can't always do backwards, and sometimes you can't do backwards because you don't have enough data for the number of predictors, so you can't fit the full model. It just will not fit. And again, it's nice. Reg subsets. So it started with the big model 3. It said, which one can I kick out here? And these all agree. They do not have to agree. Forward and backwards do not necessarily always give the same answer. And that's always a problem. You do these methods. You decide you're going to do best subset, you're going to do forward, you're going to do backwards. You come along, and then you give the results, and your collaborator goes, so which is the correct model? There isn't a correct model. You need to now look at them models. You might look at cross-validation, etc. But you have to have a discussion at some point with your collaborator that sometimes these models are equivalent and there isn't a right one. If in doubt, go for the simpler one. Unless by going simpler, you somehow remove a predictor that within the context of what they're looking at, then you would explain things better. Okay, so how do we choose our optimal model?
Can
Yes.
I ask a general question before that? which is when should you do model selection versus, like, say you've got sepsis and you've got all these genes, just identifying genes that are actually like statistically useful and or doing some kind of dimension reduction in data before doing model selection.
Okay, personally I like to get to know my data before I start doing any big fancy models. So I'll do a lot of univariate and bivariate statistics to get a sense of what's associated, and then I will build up a model from that. So I must do these models by then. I've done what you're referring to, which is what we call feature selection. So I do that quite a bit before, just because I want to get the sense of what should be in that model. And sometimes you really need to do. I'll also sometimes do dimension reductions. It also depends on the individual field. There is certain approaches and certain models that are very standard within that field. So if you're going to introduce something new, you have to make sure that it's good enough to explain. Also, simpler is better. Coming along and say, oh, we did this fancy thing, and there you are, we decided Bayesian networks were really, really good. I have had collaborators that have walked out and said, we did Bayesian networks, and everyone went, didn't understand it, got to be wrong. Because you will have that, so you do have to take into account, choose a method. So I will sometimes go to my collaborator and go, what's the standard approach to model selection in your field? And some will go, we always do forward. Fine, I'm always going to do forward. So much easier to sell. And when you're writing a paper or research, you're trying to sell your ideas to the reviewers. I like to do lots, and then we have a discussion and do it that way. I will do feature selection if it's particular data. I'll do dimension reduction. But I do find it, a couple of times I've introduced what I think is the best method, and then I've had to have a very energetic discussion with the reviewers about the validity of my approach. So, not a good answer. Stephen might have a better answer, since he actually does this more than I do. How do you decide which model to use? Which approach?
There's no rule. Is my rule. You just have to, you judge it. Yeah, like you're saying, you just play with your data until you're sick of it and you really know what's in there. Dimension reduction can be really useful. Like, so if you want to do like a factor analysis type thing and fit components, or each situation.
There's a lot more playing than people would expect. Ben?
Why would you do that forward selection ever? Like, greedy can't be the best way to pick a set of predictors out of, like the first one where it just did every set of, say, 3 predictors. That's fine if you can do it. Like, if your number of predictors lets you do it for combinatorics.
Yeah.
But if you can't, the forward must be inclined to give you like little peaks, right?
Yeah, it still works quite well. Like in this particular case, it gave the same results in every single time. I mean, I love it when I do a forward, backward, and a mix, and I all get the same answer. But I must admit, it's not right that collaborators like it. It makes sense. You go, we'll start with this one, and this was the best one, we added it in, and then we tried everything else, and this was the best one, added it in, and it seems to make intuitive sense to them. That's all.
Okay.
So, not a good answer, unfortunately. There is a little bit of an art form. Once we get the right answer, we will all stop this faffing around. Okay, so what are we trying to do? We'd love to know, we would love to choose the model that has the lowest test error. That's the test mean square error is the thing that we'd like to do. But we don't know the truth, so we can't really absolutely get that for every data in the future, so we're going to estimate it somehow. First of all, you can indirectly estimate the test error by adjusting the training error. So we can somehow take our training error, adjust it and say this is close to the test error as you do, or you can estimate your test error by using a validation set or cross-validation, which we talked about last week. So, and again, you might say, well, why don't you just go straight to cross-validation? Because it's computationally intense. Sometimes these things take time to run. So let's look at that first one. How can we adjust our measures? So the first one I'm going to look at is what's called CP. And it is just called CP. I can't actually find out what CP stands for. And in fact, the next one is just called Mallow CP. So Mallow went, oh, there's a CP, but I'm going to change it to my CP. So CP. So I've got a fitted least squares model. I've got K predictors, and the CP estimate of the test MSC is going to be basically the RSS. Remember, you take every observation, take off the fitted square, and add them all up. So these are just sort of squares. Plus, we've got 2 times K. So we've got our fit, but we've got this penalty term that basically says the more parameters you have, there's your penalty term. You're going to see that pattern all along. You're going to have a measure of fit plus a penalty term. Because we know as our model gets more and more complicated, it will fit better. So I want to sort of go, try and get a model that fits well, but try not to make it too complicated. Then your sigma squared hat is going to be an estimate of the variance of your noise term. So that's the first one. That's CP. Yes?
It's CP, so is P meant to be like the number of predictors? So it should be.
No, they just call it CP. Yeah. Yeah, no, I totally agree, and I did check that, and I've tried to find it, they just call it CP. And I'm sure at this point, Gary's got something, he goes, I don't know why, but I'm about to go and explain things. And next time I see him, he will explain exactly why it's CP. Probably by giving me a backhand. So what's that?
Your first meeting with Gary. What was that subject?
Yeah.
Yeah.
Oh, you're going to be supervised by Gary?
Yeah.
Yeah, welcome to the world of pain. Yeah. He broke his education stick on me, so he'll love seeing you. The one scariest moment was I was actually asking about a proof in my PhD, and Gary actually turned around and went, oh, this is hard. Like, fuck it, I'm walking. If you find it hard, I'm TF Bundy.
Doesn't the P refer to the number of predictors in the most complicated model?
I think the P originally was referring to the number of predictors full stop, but for some reason they've kept the CP. I've never seen it called CK, for example. I really don't know. I will try and find out more information for you. So Mallow CP, very, very similar. But now what we've got is we've got our root squared. Your sigma hat is usually made, and it's a good thing that Matt I think was implying as well, your sigma hat is usually done with the fullest model you're going to consider. That seemed to be the best estimate of the variance of your epsilon. You got plus 2k, where k is your parameter minus your number of observation points. So that's Mallow's CP. Let's see something you may have seen before. So a Kaike's information criteria. So up to this point, we've been looking at RSS as our measure of fit. Now we're going to look at the general case. So the first two we've looked at were really just in the case of least squared. Now I'm going to look at fitting to data where we're using likelihood. So remember, your likelihood is a formula that equates your data and your parameters. And a large number of procedures we see do what we call maximum likelihood estimation. That is, they take that function, they differentiate it with respect to the parameters, and then they solve to find what values of parameters maximize the likelihood. It's one of the key concepts that Fisher came up with. So it's a relationship, it's a measure of how likely is a set of parameters given that data. As opposed to normally when you think about probability mass function, probability density function, it tells you what's the probability of this data given the parameters. So you just swap how you're thinking about it. So the idea is for these models, you can actually take your log likelihood and you could substitute in your maximum likelihood estimators. So that's a measure of your fit. So that's your measure of fit term, and then now your AIC, your Kaike's information criterion, you've got your penalty for parameters, and then your term on the left, so on the right, is a measure of how well it fits. So again, we've got that concept, you've got a measure of how well it fits, and you've got a penalty for your number of parameters. The whole idea is to sort of go, this fits really well, but we're going to have to pay a price. You're going to have to compensate for models that are too complicated. And we choose the model with the lowest AIC. The reason that is there is mainly for me because I always forget. I love there's one package where it actually gives you the AIC, and then underneath it just says low ones are better. I'm like, oh, thank you for reminding me. I always have to check. There's also one called AIC corrected. Basically found that there's certain asymptotic behaviors of AIC that I'm not going to go into in this course. That's more of an advanced statistical inference course. There's asymptotic behaviors of it. And they found that asymptotic behaviors were not right in obviously small sample size, hence the word asymptotics. So they made an adjustment. And AIC corrected takes your AIC and it corrects for your sample size. The other one now is the Bayesian information criterion, where now you've still got your log likelihood. You've got k for your number of parameters, but notice before it was 2 times k. Now it's log of n. It's an adjustment for your size. You'll generally find if you're looking at your models, the BIC always seems to favour the smaller model when you're looking at them relatively. I personally have started using BIC, and again you go, well, you've given us now 4. Which one are we going to use, Jono? Seriously, it gets down to looking at the journal you're going to submit to and see what they normally use. So, a lot of times people I'll go, you should use a BIC, and they go, I don't know what BIC is. We always use AIC. Okay, that's what we'll be using. There's a little bit of salesmanship, there's a little bit of give them what they want. If what they want is not right, then you have to introduce new methodology, but then you spend a lot more time justifying it. You often become the first paper that has that in. I spent a long time explaining equivalence testing to a reviewer that explained that all my stats was wrong, and after a couple of letters he stopped asking me. We know R squared is a bit dangerous, but they invented one to try and adjust for the actual number of parameters. So remember, your R squared is your total sum of squares minus residual sum of squares over total sum of squares, which obviously you could be right in that form. The adjusted is almost identical, but you see they're now taking into account the n minus 1. So they're taking into account the size of the data and also the number of parameters. So let's look at an example. So we've got our 3 models here. I've got model 3 has a cylinder, model 2 has displacement cylinder, and model 1 has displacement cylinder in year. I fitted a model, so I've got 3 models. I put them in a list together because I was going to use map. So my map, I'm going to apply the glance function at a broom for each model. So remember that is going to return a nice little single row with a summary about that model. And it will have AIC, BIC, p-values, everything. I said .id equals model because it will give me an extra column called model, and it will give me the names of the models. So basically I'm going to get 3 rows, and each row will be summary statistics for the overall model. I don't want all of them, I want to fit on a slide, so I just selected the columns that were model, R squared, adjusted R squared, AIC, BIC. So, which one are we going to choose? You've got this output, you've gone into your collaborator, which one are you going to use?
Model 2.
Yeah, I probably agree with you. Why?
So the smallest BIC and the AIC is within 2 of the other smallest ones.
Okay, so what Josh is saying, so I must admit, I very rarely, it is a personal preference, so it's not right, it's just a personal, I very rarely use R squared and adjusted R squared. I think we had I assume that someone along my lines, Paddy or Gary or Andrew, hated R squared, and we were told every time that only plebs used it, and they weren't even clever plebs, they were sort of plebs that basically couldn't dress themselves. So we sort of believe that, although nearly every single journey we see will use this. So I'm more likely, from personal preference, to use AIC, BIC. Okay, so that's good. So remember we want lowest good. So the lowest in the AIC is the 1090, which is model 1. And Josh said, yeah, but model 2 has a 1092. Now, there's a rule of thumb that I was told by Gary, and I can't find any other justification of it other than Gary told it me, which I think is still a standard reference you can get away with. If you have 2 models, that are within 2 of one another in terms of AIC. Basically, that's within, they're almost equivalent. You have to be more than 2 before you say there's a significant difference. So if I have 2 models that are within 2 of one another, I will take the simpler model. Again, it comes down to the asymptotics. I'm sure Gary has a very good reason for this, but I'm just going to use Gary told me so. Personally, I must admit I'm a big fan of BIC. I much prefer a smaller parsimonious model if I can get away with it. So I would have gone for model 2, so I want displacement and cylinder. What else could we do to compare these models? What's the best way of getting test mean square error?
Cross-validation.
Yes. Cross-validation, there's such small models and it's so fast, you can definitely do cross-validation. That's an ideal one to do. What else could you do? I'd go back and always look at the data. Remember the important thing, significant does not mean important. If by adding one of these terms, it gives me a little bit of improvement, etc., but when I look, you can hardly tell the difference in your predictive values, especially the area you want to do. Again, go for the smaller model. It is a little bit, I'm really sorry, but that is it. There's a little bit of just looking at it, having a discussion, trying to work out what that model means in context. Oops. And that is our lecture. A nice short one, bit of a recap. So now we've got these measures. On Wednesday, we're going to start looking at shrinkage estimators. So we're going to start doing with Rich, and then we're going to look at lasso. Any questions, come and see me. We don't have an assignment due this week, it's the week after. The assignment is now up on the webpage, so please have a look at it. As I said, any problems with your marks for your assignment, please come and see me. We can have a chat about it. This week we have a workshop. This week's workshop is on RCPP and profiling. So RCPP is embedding C++ code directly in R. You need a way of compiling that code. So please go to the slides, look at the first 2 slides, follow the instructions, and then there's actually one you can copy and paste and see if it runs. If it runs, everything's fine. Because I won't have time in the workshop to get your laptop running RCPP. I'll only have time to go through examples of it. So it's worthwhile trying beforehand. Cool, thank you all very much.